Hey everyone, in this video, let's go through question 542, 01 matrix on Leetcode. This is part of our blind 75 list of questions, so let's begin. In this question, we are given an m by n binary matrix mat, and we want to return the distance of the nearest zero for each cell. The distance between two adjacent cells is 1. Let's take a look at what that means. So in our matrix over here, basically all we're concerned with is the 1 and its distance is 0. You can see that for this one, basically it's surrounded in all four directions with the 0, which is distance 1 away. So really, this does not change, and we just return the same matrix as we're passed it. And this one over here, this one, and this one are just 1 unit away from the adjacent zeros, like the closest 0, so we don't change those. For this one here, we're 2 units away, right? At minimum. 1, 2, 1, 2, 1, 2, or right and then up 2. Okay, so how might we go about doing this question? Let's think about this, right? So let me actually open my paint here, and you can ignore this, but I'll get back to this soon. But let's see. So in these types of questions, these matrix type, these grid type of questions, when we're asked to maybe, go through the matrix, find the closest, find the longest something, we have two approaches, right? We can either do a DFS or we can do a BFS approach. DFS or BFS approach, right? Now, what's the easier one to come up with? Well, the easier one might be like a DFS approach, right? Basically, what could we do? Well, first of all, we actually need to wonder, do we need to do a BFS or a DFS from every cell, or do we need to do it from a specific cell, right? Because sometimes you just need to do a DFS from the top left-hand corner. Sometimes you need to do a DFS from many items, right? Or many like cells. So here, what do we need to do a DFS from? Well, here it would make sense for us to do it from every single cell, right? That's potentially a 0 or potentially a 1. Why? Okay, well, let's say we want to consider the case for 0 first. Let's say we want to consider the case for 0. So let's assume this value here was a 0, right? If this value here was a 0. If we didn't do a DFS from every single cell, well, then we would never reach these ones at the bottom, right? The only way we reach these ones at the bottom is if we do a DFS from here, here, and then also like here, right? If we do a DFS from any of these positions at the top, we will not reach the 1. So basically, there's no like condition in which like we have to do a DFS from just one position. Here we have to do a DFS from every single 0. Now, we could have also done a DFS from the 1s, right? Maybe we did our DFS from this one and tried to find the location of the nearest 0. And then we propagated that information back to this and we filled it out. So in this case, what could we have done? Well, in this case, let's say we started a DFS from this position here. Well, then I would look in all four directions, right? I would look here, I would look here, I would look left, and I would also look right. I know I messed up those directions, but bear with me. And basically, every time I find a 0, then I know that, okay, so this is like 1 unit away. So I would record that. This is also 1 unit away. I would record that. This is also 1 unit away. So I would record that. But notice that in our DFS call, I would basically keep going, right? Like let's suppose there's like a 0 all the way down here. Well, then I would like keep doing a DFS call all the way down here to this 0. And then I would basically aggregate those results and find the minimum. And that would be my answer. So notice that we're doing like a lot of work in DFS, especially on the larger grids. Okay, so DFS is maybe probably not the best option here. Let's consider BFS. Okay, so how do we do a BFS? Well, in a BFS, and again, we have to consider whether we want to add in all of the cells or we want to do a specific cell, like a specific number, right? Well, here again, we have to add in all of the cells, right? Because it's possible that this value here is a 0. And if this value is a 0, if we did like a BFS from here, well, here, we wouldn't basically expand, right? Because all of these are 0. We don't want to explore more zeros. We want to find the closest 1. So in this case, right, like, so if I did a BFS from here, it wouldn't lead me anywhere. Same thing for this, same thing for this. The only BFSs that are meaningful for us is the BFS from this location, and from this location. So basically in our BFS call, we would have to add in multiple items. Okay, so that makes sense. Now, what's another reason why we might want to do a BFS? So let's maybe think about this, and this is actually why I have this thing over here. So let's maybe think about this. So this is a pond, right? And these are like ripples on a pond. You can maybe think like I'm throwing rocks or something, and I form these ripples. So let's assume that, what do I want to assume here? Okay, let's assume that this location here, right here, this is a 1. Okay, this is a 1. And let's assume that I do my BFS calls from all of the zeros. So all these centers here are 0. This is a 0. This is a 0. This is a 0. This is a 0, etc. Now, what do we know about BFS? Well, we know that BFS is breadth first, right? It expands breadth first. What will happen? Well, this 0 here, it will try to expand like this. it will expand further, it will expand further, etc. This one here will also expand further, expand further, expand further until we reach a 1. And same thing over here. This one will also eventually reach this one over here, right? It will reach this one over here. Basically, the point I'm trying to make is that in BFS, what we know is that the closest element, in this case, the closest 0 to the 1 will actually reach the 1 first, right? This value here will reach the 1 first compared to this one all the way here. Same thing over here. This one will reach further. It will take a longer time to reach this one compared to this 0 over here. So what does that kind of tell us? Well, that tells us that if we start our BFS call from all of these zeros over here, every single one of the zeros, then what can we do? Then our BFS call, if we start it and we do it level by level, right? So what does it mean level by level? Well, by level, it means that we consider one level at a time. So in our BFS call, initially, we will have all 5 of these zeros, okay? All 5 of these zeros. So then what will we do? Then we'll go ahead and we'll perform our BFS call for all of these. Well, this one won't perform. This one will perform. It'll go down. This one won't perform. This one will perform. It'll go over here. Okay, so that's our BFS call. And this is kind of the second level, right? This is the second level. Now note, whichever one of these BFS calls reaches this one element here first, that will be the correct one, right? Like that will be the first one that reaches it. There might be like a 0, like all the way. Like let's suppose this was a 1, right? Let's suppose this was a 1, and maybe there was a 0 over here. For this 0 over here, it would actually take like, and let's suppose actually this was also a 0, okay? So for this 0 over here, it would actually take 2 steps, right? To reach this 1. First, it would have to, well, let's actually assume, so let's assume this one was a 1 here. Let's assume this one was a 1. Okay, so for this 0 over here, first thing it would have to do is that I have to do a breadth first search to come over here. And then once it's over here, it would do another breadth first search to come over here. But notice that this 0 over here can come here in just one go. So it's kind of similar to what we have in the pond. Here we have our central one. Here we have surrounding BFS calls. And notice that the closest one will arrive at this BFS call first. And so if we know that the closest one will arrive at the BFS call first, then we know the closest distance, right? We know the shortest distance. And so whenever we process a BFS level by level, then we know that we're going to arrive at the closest location first. Whichever BFS call arrives first, that will be the shortest distance. We know that. Okay, so we've established that we want to use BFS. We established that we want to add in all of the elements. Now, why am I adding in the zeros? Why don't I add in like the ones initially? Well, I actually could add in all of the ones. I could actually do a BFS call from here and then figure out which one is the closest 0. The problem with this is that, for example, let's say I'm over here, right? Let's say I'm over here and I expand sideways. And now I'm at this 0 over here. Okay, well, I know that this distance is like a distance of 1, right? But now I'm currently on this cell over here. I'm on cell 01, 012. I'm on cell 012. I have no idea that this cell was called by this one over here. I have no idea that I need to update this cell over here. Maybe I can store that information somewhere, but really that's not needed, right? Because if you think about it, if we just go ahead and start off at the zeros, if we start off at all the zeros, then whenever we reach this one here, then we know 2 things. First of all, we know the shortest distance, we know the level, and we also know which cell to update, this cell exactly here. So basically, you can think about it like the cell that you want to update, you don't want to add that to the queue. Instead, you want to add in the other cells, and so you can find the shortest distance. And so when you're finally at the cell, you can update it with your level. Okay, so let's take a look at how we can do this in code. I think it'll make more sense that way. And so let's begin. First of all, I like renaming these to grid. It's just personal preference. So first I will define my rows and my columns like so. Length of grid and length of grid at 0. Now I need my queue. Right. What else do I need? Well, now I need to loop through my rows and loop through my columns. And for the items that are 0, I want to add them to my column. So if grid at row and call is equal to 0, I will add them to my queue. Row and then call. Okay, perfect. So now what do I need to do? Well, now I can go ahead and I can loop through my queue, right? And remember, we want to process queue level by level. So what does this mean again? If this is, let's assume that we have like a binary tree. It's probably easier to understand. Let's suppose we have a binary tree. And we have something like this, right? We have something like this. We have something like this. Initially in the queue, we just have this element, right? We just have this element in the queue. Then what we do is we go ahead and we add in our two children, but we only process this first one. When we add in our two children, we will go ahead and only process this level. We will only process this level. Notice that when I actually process this node, I will add into the queue, I will add in these two elements here. I will add in these two elements here, but actually, I'm only going to process these two elements. I will not process this, and this, because that would indicate that all four of these are on the same level. They're all the same distance away from this node up here, which is not correct. So that's why we're going to process level by level. And how we can do this is we can find the size of the queue. And the basic, we can just loop through and we can just do it based off of the size, right? Okay, so we have this information. Now what do I know? Now I can pop from the queue, so I can do row column, you go to queue.pop, 0. And now I know if I arrived at a 1, this has to be the shortest distance, because we argued over here, like if we're at the pond, if this is the 1, then whichever BFS call arrived here first, it has to be the shortest distance. Okay, so I need to basically set grid at row and call equal to level. Now what is level going to be? Well, level can start off as 0. And here, basically every time we're done this iteration, every time we are done this loop here, every time we process the queue, we increment level, we increment our distance. So basically here, like every time I finish this one call here, so maybe if I was to kind of draw this again, every time we finish this, so every time we process this first level here, this first level here, this first level here, now we're all visiting nodes that are 1 distance away. So now I can process the nodes that are 2 distance away, etc. So that's basically what I'm doing in my code. Okay, so now we increase level, we do that at the very end. Now, if grid at row and call is not 0, right? Like if it's not 1, if it's either 0 or if it's like a number like 2, then what do I know? Well, if it's 0, I know that I don't want to visit this cell, right? Because I already did my BFS from all of the 0, so I don't need to visit any more zeros. If it's a number like 2, well, then what does it mean? Well, it means that this cell already has the shortest distance of 2, in which case I'm not going to touch it. I'm not going to add it to my queue. Okay, so if this is all good, what do we need to do now? Well, now we need to go through top, right, left, and down. We need to go through all 4 of the directions. So how we can do this is we can just create this. This is like a interesting trick. So basically, I add in like the deltas here. So I would just do 0, 1, 0, minus 1, 1, 0, minus 1, 0, right? And then I can do for dx, dy, and dirs. Then I can do something like new row is equal to row plus dx, new call is equal to row, or is equal to call plus dy. And now I need to check, first of all, that I'm not out of bounds, right? And we have our way of doing this. We always check if new row is less than 0, or new row is greater or equal to rows, or new call is less than 0, or new call is greater or equal to calls, then what? Well, then we'll just continue, right? Because this is an invalid point. It's outside of our grid. Otherwise, what? Well, we have to check if we've like visited this place before, right? Because it's possible that this 1 over here, we've already visited from this BFS call, but we can also visit it from this BFS call, which will be longer, but we can also visit it. So we need like some sort of scene variable, as we often have in queues. So let's go ahead and add in our scene here. So we will add in scene as a set here. And then initially, because I add in all of these to my queue, I will add them to my set as well. So call, okay. And this will actually make sure that like if I'm at like a 0 here, I don't want to go leftwards towards another 0, right? So it will stop that. So actually we can just do the check over here. So what we can do is we can do if grid at new row, new call is equal to 0, then we just continue, right? We don't actually need to add it. So technically we can just omit this here. But what we do need to do is we need to check that this new row, new call, this should actually be new call. We have to check that this is not in scene, right? Because if it is in scene, then we've already visited, we've already established the shortest direction, so we don't need to visit it that again. So if new row, new call, not in scene, then we're going to go ahead and add it. So we will do scene.add new row, new call, and then we'll add it to our queue, new row, new call, and that's pretty much it. And so after this, we can just go ahead and we can return our grid, because we're modifying the existing grid. We're not creating a copy, we're modifying the existing grid. And so let's go ahead and this. Let's run our sample test cases. Perfect, let's go ahead and submit. Perfect, so it works. So one thing I'd like to mention here is that if we didn't want to kind of follow this like syntax of like going level by level, right? There is a different way in which we could do this. And essentially what we could do here is, instead of just appending row and call and like calculating the level based on like the way we do our queue operation here, we could actually just add in one more field, which we can just call the level. And so how this would work then is that here I would pop out the level as well. And so I don't need a level here, and I don't need any of this, and I don't need this either. I can push this all back one. But basically what I need to do here is when I'm appending, I will append level plus one, right? So that's like another way we can think about doing this. But I like the other way better. It just kind of makes more sense to me. But this is like another way we could do it. We could append the level as part of the queue itself. So you don't have to do anything fancy like in the queue itself here. But anyways, yeah. So what is the time and space? Well, time and space basically just be m times n, right? We're just going through the matrix, and we have our space as well for the queue. Okay, so that was this question. Thanks for watching.